Welcome viewers. Today we will be talking on vitamin D. Vitamin D is a fat-soluble vitamin, the other ones being vitamin A, E and K. A striking feature of vitamin D is the fact that vitamin D is synthesized in human skin upon exposure to sunlight, and that's why vitamin D has a nickname, the sunshine vitamin. However, vitamin D is still considered as a vitamin because vitamin D was discovered the way many other vitamins were discovered. That is, when it is absent in the diet, certain disease symptoms appear, and upon administration, the disease symptoms are cured. We will discuss all the aspects of vitamin D in details, but for the time being, let's focus on its discovery. In the year 1917, Elmer McCollum of USA discovered a principle in cod liver oil which was later proved to be vitamin A. McCollum found that feeding cod liver oil to dogs suffering from ricket could cure them. So everybody thought that it was actually vitamin A which was responsible for the observation. But in the year 1922, McCollum came out with a modified cod liver oil in which vitamin A was completely destroyed. He could show that this modified cod liver oil could still cure rickets in dogs. So he concluded that there must be some other factor or factors in cod liver oil other than vitamin A which was responsible for curing rickets in dogs. In the year 1928, Adolf Otto Reinhold Windaus of Germany got Nobel Prize in Chemistry for his work on the constitution of sterols and its involvement with vitamins. In 1971 and 1972, Michael Holick of the University of Wisconsin-Madison discovered all the metabolic activation, inactivation, and most of the biological actions of vitamin D. Let's look at the structure of vitamin D. A vitamin D has a steroid type of a structure. The mother compound is called guanine, which is a C17 compound which has 4 rings A, B, C and D without any alkyl substitution to it. C18 compounds are called estrane, and estradiol is physiologically important compound in that class. C19 is androsterone, C21 is pregnane, C24 is choline, and C27 is cholesterol. And in cholesterol class, the physiologically important compound is called cholesterol. And cholesterol is actually the mother steroid of all the vitamin D compounds that we know. Structurally, vitamin D is actually a secosteroid. A secosteroid differs from steroid in the fact that in secosteroid, the B ring of steroid backbone is broken, whereas the A, C and D rings are still intact. The two major vitamins of vitamin D that are physiologically most important are vitamin D3 or cholecalciferol and vitamin D2 or the argocalciferol. These are collectively called the calciferols. The other vitamins of vitamin D are vitamin D1, which is a 1:1 mixture of argocalciferol and lumisterol, vitamin D4 or 22-dihydrocalciferol, and D5 or cetocalciferol. These compounds are physiologically less important than vitamin D2 or D3. Foods rich in vitamin D are rare in nature. However, cheese, margarine, butter, fortified milk, healthy cereals are important sources of vitamin D. However, still the richest source of vitamin D are the fatty and oily sea fishes. The recommended dietary allowance of vitamin D is 400 to 800 international unit, which is equal to 10 to 20 microgram, because 1 microgram is equivalent to 40 international units of vitamin D. Vitamin D requirement of body varies depending on the age of the person as well as the gender, and the deficiency disease associated is ricket in the case of children and osteomalacia in adults. The richest source of vitamin D are the oily fishes, which include the cod fishes, the herring fishes, the channel catfishes, and the salmons. Now, the recommended dietary allowance or daily intake level of vitamin D varies depending on the parts of the globe. For example, in USA, for children and infant, the limit is 400 international unit. For adults, it is 600 international unit. For aged, 800, and for pregnant and lactating women, it's 600 international unit. The recommendations of Canada is same as that of USA, while for Australia and New Zealand, the RDA is bit lower side, which is 200 international unit for children and infants and 400 to 600 international units for adult, aged, and pregnant and lactating women. In India, the recommendations are a little bit higher, because in India, the staple food is mostly carbohydrate based, which is very poor in vitamin D content, and it has been seen all over the world that ricket is profoundly present in the developing countries. That's why in India, RDA is 500 international unit for infant and children, and for adult it is 500 to 800 international units, and for pregnant and lactating mothers it is 1000 international unit. It is important to note that since vitamin D is a fat soluble vitamin, over ingestion may lead to problems, because urinary excretion may be poor and it may get stored in the body and hypervitaminosis symptoms may crop up. That's why many countries have set a tolerable upper intake level for vitamin D, which 1000 international unit for infants, 1500 to 3000 international units for children, 4000 international units for adult, aged, and lactating women. This tolerable upper intake level is more or less similar in different parts of the globe. If you look at the synthesis of vitamin D, we see that vitamin D is produced from the precursor called 7-dehydrocholesterol, which in presence of sunlight gets converted to vitamin B3 or cholecalciferol, which eventually gets into the blood. Now, if you look at the electromagnetic radiation spectrum, we see that ultraviolet ray, which causes this transformation of 7-dehydrocholesterol to cholecalciferol, is UVB, which is 280 nanometer to 315 nanometer in wavelength. It has been seen that 290 nanometer is the best effective for synthesis of vitamin D3. Vitamin D, whether ingested from food or synthesized in the skin, is physiologically inactive. It needs metabolic activation. Metabolic activation of vitamin D happens by two sequential steps of hydroxylation. The first one happens in liver and the second one happens mostly in the kidney and in some immunocytes. In the first step in liver, vitamin D25 hydroxylase, and in the second step, the hydroxylation happens at C1 alpha position to form 1,25-OH2 vitamin D3 or calcitriol which is the biologically active form of vitamin D. However, Michael Holick has shown that if hydroxylation takes place at C24, vitamin D is rendered completely inactive both in vivo and in vitro assay system. Another important fact of vitamin D is that vitamin D in plasma doesn't circulate free. It remains bound to a protein called vitamin D binding protein. In human, vitamin D binding protein is coded by a gene called the GC gene, which belongs to the albumin G superfamily, and vitamin D binding protein is mostly alpha helical in conformation. So to summarize the metabolic activation and inactivation steps, I reiterate that vitamin D is either synthesized in the skin as cholecalciferol or ingested through food, becomes bound to vitamin D binding protein in the plasma, which eventually gets into the liver to become 25 hydroxy vitamin D3, which once again comes back to plasma and reaches the target tissues like the kidney or the immunocytes or in the brain or in the prostate gland to produce 1,25 dihydroxy vitamin D3 or calcitriol, which is the metabolically active form of vitamin D. The deficiency disease associated with vitamin D is ricket in case of children and osteomalacia in case of adults. You can see these are some of the bone deformities that are produced because of rickets. In rickets, because of low calcium content of the bones could not bear the weight of a growing baby. Hence, these deformities take place. In the case of osteomalacia, which is characterized by low bone mass and structural deterioration, since vitamin D is involved with the normal homeostasis of calcium and maintains an equilibrium between serum calcium and bone calcium, in absence of vitamin D, there is significant loss of calcium and phosphate from the bones, and the bones become softer and fragile. So the characteristic features of osteomalacia are the defective bone mineralization, porous bones, the bones become more fragile, and there can be structural deterioration and quality of the bones. Over the last 20 or more years, lots of researchers have claimed many functions or effects of vitamin D. However, much more research is needed in this field to confirm these effects of vitamin D. However, in this class today, we have divided the functions of vitamin D into its classical function as well as its non-classical functions. The classical functions of vitamin D is its role as a hormone to maintain the calcium balance and homeostasis of the body, and its role in bone metabolism. And the non-classical function of vitamin D includes its immunomodulation role, its involvement with heart and cardiovascular system, glucose metabolism, multiple sclerosis, its involvement with cancer and cellular growth and differentiation, as well as the mental health. Molecular role of vitamin D is to act as a hormone. Vitamin D in its biologically active form, that is 1,25 dihydroxy vitamin D, enters into the cell, into the nucleus, where it binds to its nuclear receptor, and being aided by RXR or the retinoic X receptor, it goes and binds to the upstream sequence of many genes and act as a transcription factor and upregulates or downregulates the transcription of those genes. So all the biological actions of vitamin D are mediated through its action as hormones. be it the classical functions or the non-classical functions. For example, for the classical functions, it increases the calcium uptake simply by increasing the transcription of the receptors that are involved in calcium uptake in the intestine. It maintains calcium homeostasis by parathyroid hormone synthesis. It also increases the renal phosphate and calcium uptake the same way it increases the calcium uptake in the intestine. And in bone metabolism, it directly affects the growth and development of osteoblasts and osteoclasts. The same way, non-classical functions of vitamin D is mediated by controlling the transcription of certain genes. The target cells of vitamin D is primarily the liver, where it gets converted to 25-hydroxyvitamin D, and finally it reaches into its ultimate target. It may be the kidney, where it is mostly converted to 125-dihydroxyvitamin D and involved in the calcium homeostasis, its immunomodulation role, its control of blood pressure and bone health. To a little extent, it enters into the monocytes and macrophages, where it is once again converted to its biologically active 125-dihydroxyvitamin D and mostly involved in immunomodulation function of vitamin D. And finally, to a very small extent, vitamin D reaches the prostate gland, the breast, colon, lung and keratinocytes, and once again it is converted there to its active 125-calcitriol form and regulate the growth and differentiation of these cells. Finally, we reach at the take-home message for this class. Vitamin D is a fat-soluble vitamin. Very few foods naturally contain vitamin D. The richest source of vitamin D are the oily fishes, namely the cod, herring, and salmon. Vitamin D is synthesized in the skin upon exposure to sunlight, especially the UVB part of it. Vitamin D deficiency in children causes ricket and osteomalacia in adults. Chemically, the two important vitamins of vitamin D are vitamin D2 or argocalciferol and vitamin D3 or cholecalciferol. Vitamin D, whether ingested from food or synthesized in the skin, needs sequential hydroxylation for its biological function. Hydroxylation of vitamin D2 and vitamin D3 at its carbon 1 and carbon 25 makes it biologically active, whereas hydroxylation at C24 renders vitamin D into its biologically inactive form. Vitamin D in plasma always remains bound to vitamin D binding protein. The major function of vitamin D is to maintain calcium metabolism of the body and bone health. Other functions of vitamin D include its role as an immunomodulator in maintenance of good cardiovascular and muscular health, its role in multiple sclerosis, cellular differentiation, cancer, and in mental health. Thank you.